Morning. Are you able to hear me now?
Yes, sir.
Okay, good.
We can hear you.
All right. So I guess you have already seen the slides. Let me just quickly go over the slides and then we will have a discussion afterwards. So let me share. Okay, are you able to see the slides?
Yes, sir.
Great. So let me just quickly run through them, and in between I will also switch to another presentation just to show you the kinds of microstructures. So we'll start with precipitation. And just one slide, just to conclude everything that we said in the previous class. So the main point that I want to make is this precipitation in liquids and solids. And as we said in the previous class, in the liquid, usually there is a density difference. If the precipitate, whether the precipitate is a solid phase or a liquid phase, it would have a density which is different from that of the parent liquid, and then because of that, it would either sink to the bottom or float at the top. But in the solid state, such a thing is not possible. So wherever the precipitate is nucleated, it just stays put, and that's great. And that is basically what we want in a solid, and because we want to create these precipitates for a specific purpose, and we want them to stay there. And so this makes it possible. The other main difference is in terms of diffusion. Remember, to produce a small solid of sugar from a sugar solution, you need to consolidate a lot of sugar molecules from the surrounding liquid and bring it to that one place where they all have a chance to solidify. And that requires diffusion, and the diffusion in the liquid is much faster, and that is one reason why one is able to do all kinds of interesting videos on fluid dynamics phenomena involving diffusion. So I don't know if you have seen this website called FY Fluid Dynamics, and it has all kinds of videos on all kinds of really beautiful things that one can do in real time. And in some cases, if it is a little slower, then you just need to use a speed up of maybe 2x or 4x, and you'll still be able to see it. Whereas in the solid state, I mean, things take a very long time, and you have to wait for days and days to see stuff. First of all, in many cases, you may not even be able to see stuff because it's all buried inside the material, and you have no direct way of looking at them. And B, they're also extremely tiny. Even for producing such tiny things of the order of micron or less, you would have to wait for a long time. And that is another reason why, I mean, you don't have all kinds of interesting videos of things like precipitation in on YouTube. But there are some, and as we go along, I'll try to get to some of those videos. You will see some videos of simulations, but there is really nothing better than actually watching some real stuff from real material. So the diffusion gives you the lower limit on the temperature at which this precipitation can happen. Remember, the upper limit is given by the solutionizing temperature, that is the solvus temperature for a given alloy, above which everything goes into solution and so on. Whereas, usually if the diffusing species is a substitutional solute, such as aluminum and nickel, then usually there is a lower limit to the temperature above which diffusion is appreciable. Rather, more importantly, below which diffusion is basically extremely sluggish. And for nickel, whose melting temperature is of the order of 1400 plus degrees Celsius, which is like 1800. So 0.5 of that would be about 850 to 900 Kelvin. And so typically below about 600 to 650 Kelvin, degrees Celsius or so, you can expect pretty much nothing. So if you're able to quench it down to low temperature without causing any transformation, then it will just stay there for a very, very long time. If the solute, on the other hand, is interstitial, such as carbon in iron, for example, you can push this limit down to about 25% of the melting temperature, approximately. And so you can still see some activity in steels, for example, produced by diffusion. You can get precipitation to happen in certain kinds of steels in specific circumstances at temperatures as low as 200 degrees Celsius. Okay, I just want to switch to something on microstructures. This is a general purpose set of slides that I put together. And one of the things that really interests me about materials is the fact that they possess microstructures. And the way I sort of motivate this is by showing this this piece of art. This guy called Yves Klein became famous for producing art of this kind. And just do a Google for him and look at this. This IKB stands for International Klein Blue or something. So that is the color that he came up with. And this art piece has a number 81. So you'll find a whole bunch of others there. And they're all sort of various shades of blue. And there is a really no internal structure to it. But I still have no idea why people go gaga over such a thing. But this is a celebrated piece of art. And it is celebrated precisely because I think it has nothing. So if you have a perfect crystal, for example, then it would be like Klein's piece of art. And it is sort of interesting. It does certain things and for you, for the material. It produces certain kinds of symmetry and so on and so forth, which is exploited. In some cases, you actually want defect-free crystals. But what makes materials far more interesting is the fact that you have all these defects. And in microstructure, the defects that we are talking about are the interfaces, the walls between different phases. And so we'll just go through, and many of these interfaces are produced through precipitation. So we will just run through a set of microstructures in various kinds of alloys produced through such a precipitation route. And this is from superalloys. As I said, the nickel aluminum binary is a prototype for developing superalloys, which make modern jet engines even possible. And the kind of temperatures that you go to inside these engines, it is pretty close to the melting temperature. And then for materials to retain their integrity at that temperature depends on development of these strong materials which retain their strength at such high temperatures. So here's a very interesting series of the white regions are the precipitates, and of course the black regions are the matrix phase from which they precipitated out. And so because of underlying symmetry and elastic interactions between these precipitates, they sort of line up along specific crystallographic orientations. This entire thing is from one crystal, one single crystal. Rather, you can think of it as from within one grain. And look at the micron marker here, it is 1 micron or so. So the extent of these, the size of these precipitates is anywhere between 100 nanometers, this small thing here, to about half a micron, 500 nanometers or so. And So these precipitates which are produced through heat treatment, they are the ones that impart this strength at high temperatures. And so we will look at mechanical behavior in the next set of lectures. So let me just quickly run through the remaining microstructures. This is yet another nickel aluminum moly alloy from another study. Again, you can see that these nice alignment of particles. And again, the micron marker gives you an indication about the size of these precipitates. These are extremely tiny, and you cannot see them using optical microscope. You need SEM or TEM to be even able to see such tiny structures. This is from a computer simulation, so I'll move past it very quickly. There is nothing interesting here. It basically says that at least we understand the main reasons for the alignment, which is the elastic interactions among particles. Okay, this is yet another nickel aluminum alloy from another study. So here the molybdenum content is changed in a systematic fashion as you go from this microstructure to this microstructure. The main difference is the fact that the elastic interactions are promoted with a certain amount of molybdenum in the alloy. And as you move systematically away from that level of molybdenum, you basically remove the elastic interactions and the particles acquire spherical shapes. The other thing that happens is the amount of volume, the volume occupied by the precipitate phase. Here it is, more than half the volume is occupied by the precipitate phase. Here it is, I don't know, maybe less than 20%. So that again is something that is controlled by the controlled changes in the composition in terms of the molybdenum content. Anyway, so let me quickly run through. This is another class of materials. These are basically for fundamental studies. So here the structures take on this checkerboard structure, which again is sort of interesting. But COPT alloys by themselves, I don't think they are particularly useful technologically, but they provide a way to check our understanding of why certain kinds of microstructures are promoted over certain other kinds. This again has something to do with elastic string. Okay, this is one of my favorites, and this is from titanium aluminum niobium alloys. And this is my favorite for many reasons. One of them is that this class of alloys were discovered, and the specific precipitate phase here, called the O phase, was discovered at the Defense Metallurgical Research Laboratory by this set of people. One of them, D. Banerjee, is now with us in our department. So he moved from DMRL to IISc about 10 years ago. And what you see here, the surrounding stuff is basically the original matrix phase from which you are producing the precipitate. And the precipitate can come in 3 different crystallographic variants. If that doesn't make any sense to you, don't worry. It is basically the same phase, but 3 different orientations of the crystal. The matrix phase is hexagonal, and the product phase here is orthorhombic. And orthorhombic has only 2-fold rotation about the c-axis, whereas the hexagonal has 6-fold rotation. Therefore, there are 3 different ways in which the precipitate can be created within the matrix. And they have their own misfit and so on. And what is interesting is the fact that they all, at least in certain composition ranges, they are produced in this really nice form. And as you can see, this is essentially the Mercedes-Benz logo. And that is one of the reasons why it is one of my favorites. And of course, yet another reason why it is a favorite of mine is that in our lab, we did some computer simulations to study the formation of such microstructures. That was done by Shashwata Bhattacharya, who was a student in our group, and he is now a faculty member at IIT Hyderabad. And we could see things of this nature produced under specific circumstances. And of course, those circumstances in simulations were created to mimic what happens in the real alloy. And when we saw this, we were quite thrilled that at least our understanding is on a firm footing. And of course, real alloys have several other complicating factors which we did not explore. That's a different story altogether. But the microstructure itself is visually quite pleasing. And again, in the same class of alloys, again from the same work done by Muralidharan and Banerjee and others, one could get all kinds of other interesting features, and those are also reproduced at least at some level in our simulations. Right, so yet another set of microstructures from the same alloy at a different time. And we now move to another class of materials. These are cobalt-based superalloys, and they are a contender for certain specific applications inside jet engine. They have a lower density, they give you that advantage, and they also have at some level better corrosion resistance for a specific kind of corrosion. I think it is attack by sulfur or something, I'm not very sure. And so this field itself is pretty young, and we have at least 2 or 3 people in our institute, and of course several other groups in rest of India who are at the leading edge of development in these alloy systems, cobalt-based superalloys. I think I already mentioned their names last time. It is Professor Chattopadhyay and Professor Makineni from our department, and they are leading a program in which there are partners from other institutions in India. So, I'm not very sure how much longer it would take before they are deployed in a real turbine. But when they are deployed, I think the contribution from India will have played a major role in the development of those alloys, which actually make it to the application. All right, this is yet another microstructure from the class of cobalt-based alloys. And I want to show this because this is from 2005 or so. This was one of the first studies to show that it is possible to produce microstructures which are similar to those found in nickel-based superalloys, and therefore could potentially replace nickel-based superalloys in certain specific locations inside the turbine. Okay, this is again a model alloy. Again, I don't think this is particularly useful, but as a model alloy, it is useful because again it allows us to test our ideas on our understanding of these phenomena. Again, this is from nickel-3 germanium, nickel nucleates and then grows, and you see all those nickel particles in different forms. They are elongated along specific crystallographic directions. Again, look at the micron marker here. It's about 300 nanometers or so. So the width is about 100 nanometers. The length is about 300 nanometers. Again, yet another microstructure here. And this is from a class of titanium alloys based on titanium, aluminum, and vanadium, which is the workhorse material among titanium materials. And again, there are all kinds of precipitates, and there is a grain boundary here. So here is one grain, here is another grain. And again, the micron marker here is here. And I'm not very sure what the length scale there is. I'm not able to see it that clearly. But anyway, so I've given the reference here. And it's pretty neat. So you see all these elongated plate-like precipitates, and they appear in this form because what you're seeing is basically a section, and in the section they appear like these rods. Here's yet another precipitation situation where the precipitation has happened primarily at the grain boundary. Inside the grain, nothing much has happened. And this is mainly because of the difficulty of nucleation that we have already talked about. And this is a classic case of heterogeneous nucleation happening at the grain boundary. Here's yet another situation involving some other titanium alloy. And here's a grain boundary and the precipitates. In this case, they are plate-like precipitates, and they seem to be created at the grain boundary, and they're all sort of growing into the matrix. Pretty neat microstructures. Again, this is the scale of the microstructure, and but in terms of thickness, which is the relevant length scale here, those would be of the order of a micron or less. Extremely thin plates. And the other thing that you can see is the orientation of these precipitates. Inside that grain, they're all generally parallel, and inside these grain, the white regions, they're all nice and parallel here. And there is another set of things that appear in black, and they're also sort of parallel to each other. Very, very nice stuff. And this is a very interesting study, rather recent, from 2011 or so. And again, the micron marker here is 100 nanometers. So these are extremely tiny things, about 10 to 20 nanometers or so in size. They are nice and spherical. That is one thing that you see. And the second thing that is very important, which they proved using very careful microscopy, is to show that they are actually in the form of core shell particles. The core is based on aluminum scandium compound, and the shell is based on the aluminum lithium, some aluminum lithium compound. And so you could use heat treatment to produce this sort of core and shell type precipitates. Really, really nice stuff. And so aluminum copper alloys, again, are an interesting class of alloys. We will discuss the importance of aluminum, copper, and related materials a little later. Again, you see all these really nice, interesting plate-like precipitates within this material with this type of size. Here it is 200 nanometers, and here again 200 nanometers. The thickness is of the order of 10 to 20 nanometers or so, and the plate dimensions are again of the order of 200 nanometers, the plate length. Really nice stuff. So I just wanted to show you this before we move on to the remaining part in steels. We've already seen the eutectoid transformation and the kind of microstructures that it produces. It produces lamellar microstructures. This is just a quick recap. I won't go through these things. The transformation itself is from gamma with this composition, which is about 0.8 weight% carbon in iron. If you go to the high temperatures about 727 degrees Celsius, what you have is a single gamma phase, which is FCC. And if you cool it to below the eutectoid temperature, you expect alpha and Fe3C. They have a name. Alpha is called ferrite and Fe3C is called cementite. And this gamma itself is called austenite. Ferrite comes from iron, I suppose. And the cementite, I have no idea why it got its name. And austenite is based on the guy who did some early microscopy called Austen, I think. All right, so we get this lamellar microstructure. Here is the lamellae. And using lever rule, you can arrive at the ratio of the thicknesses of these lamellae, which should be in the ratio of 1 to 7.5. 1 is for cementite and 7.5 is for ferrite. And we also showed that the arrangement, just like in the case of eutectic, the lamellar arrangement allows for migration of easy migration along the boundary between the colony and the parent phase. Along the boundary, diffusion of carbon takes it to the right locations. Here in this case, a cementite, which is carbon rich, which requires carbon. So austenite, which has some intermediate carbon content, this allows for carbon to migrate along the boundary to cementite, so that cementite can grow. And these regions, because they are losing carbon, the composition of gamma there goes more and more towards ferrite, and therefore ferrite can also grow quite nicely. And this sets up a very nice cooperative mechanisms by which both of them can grow. And here's a set of microstructures that I got from the next chapter in Callister and Redfish. So you see very coarse microstructure, very coarse pearlitic microstructure. This alternating lamellae, that microstructure has a name and it is called the pearlite. And if the transformation happens at a lower temperature, then the size scale of pearlite becomes pretty fine. And here the interlamellar spacing is of the order of a micron or so. And since optical microscopes have difficulty resolving features which are separated by about a micron or less, you see black blobs here, primarily because the features have become really tiny. And so the simplistic explanation, I mean, this is this characteristic lamellar spacing. It is typically smaller at a higher undercooling. That is, the transformation happens at a lower temperature. And so why does it happen? I mean, the actual explanation is a pretty complex one, and it is still a matter of research to figure out, I mean, the full extent of the complex interplay between several factors. I mentioned only two of them here, the driving force and diffusion. So it is called pattern formation. It's this sort of studies are undertaken by people in many different fields, physicists, mechanics people, and some chemists and biologists as well. So if you want to know why biologists may be interested in something called pattern formation, I'll give you two examples. The skin of tiger has a characteristic pattern, and of course that pattern is different from the skin of leopards and cheetahs and so on and so forth. So what you see on the tigers and cheetahs, they are basically patterns. If you think of them as patterns, then, and they are at some level biologically determined, and the chemical origins of such a thing was something that was explored by Turing, the same Turing who is very famous in computer science. And so you can take a look at this classic study in which he used a class of models called diffusion. What is it called? I forget the name. I'll send you the name in the comments later. And so he did a study to show that with just two nice differential equations, if you solve them numerically, you can generate a whole range of patterns. Some of them look like tiger patterns, some of them look like cheetah patterns, and so on and so forth. Because of which, I mean, that class of models are still being explored. Okay, let's just move on. Hypoeutectoid steels and hypereutectoid steels. They are basically on either side of the eutectoid. If you go to lower carbon content, they are called hypoeutectoid. And of course, they undergo first the formation of ferrite before the pearlite transformation happens. So the formation of a ferrite typically happens along the prior austenite grain boundaries. You can see this necklace-like thing surrounding the surrounding each austenite grain. And the interior eventually undergoes this pearlitic transformation. And on the scale, it is so fine that you are unable to resolve it. Here, the microstructure itself is purposely taken using a low mag, and the pearlite interlamellar spacing, which is of the order of maybe about 10 microns or so, or smaller. They are too small here to see. You can also go to the other side. In this case, cementite precipitates out first, and you see these thin regions of cementite, basically like a necklace around each austenite grain, and the interior undergoes the pearlitic transformation later. I mean, given what we know, I mean, we are able to explain these features quite nicely. So just like in precipitation, these pearlite transformation also requires diffusion, and because of that, there is a lower temperature at which this pearlite transformation does not happen anymore. But something else happens. We will look at that. But let's at least look at the framework that allows us to understand various observations in steels. That framework is in the form of these so-called time temperature transformation diagrams, shortened to TTT diagrams. And so this is for a eutectoid steel. So you have a diagram for each steel that you develop. So you do some basic studies and develop those diagrams. And the studies themselves are fairly straightforward conceptually. Of course, experimentally, they're all difficult to execute. Basically, you take the alloy to the single, this is on the y-axis, what you have is a temperature. So above 727 degrees Celsius, you are in the single phase austenite regime, and you quench it very fast to some temperature and hold it there. And you take many samples and hold them all at this temperature, let's say 600. And at different times, you take them and quench them to low temperature and then look at what you have in the microstructure. And so the red curve here tells you the first appearance of pearlite. That is pearlite as an alternating lamellae of cementite and ferrite. And the green curve here represents the time at which the entire microstructure is already filled with pearlite. There is very little austenite that is still left. So during this intermediate time, so the x-axis is time on a log scale. So during this time, I mean, you have the pearlite formation from austenite. So they are, like I said, empirically determined diagrams, which is okay. I mean, we can still make sense of these things. And this particular figure is for the eutectoid steel. The transformation starts very late. I mean, the high temperature behavior is very interesting. Asymptotically, it approaches the eutectoid temperature asymptotically as time tends to infinity. So the start also goes to infinite times as the temperature transformation approaches the eutectoid temperature. And like I said, in the case of precipitation, as you come down to lower and lower temperatures, carbon diffusion becomes more and more sluggish, and therefore things become slow. And therefore, if you look at what happens in these steels, nothing much happens until later times at low temperatures as well. So in between, there is this nice sweet spot, and this N represents the location called the nose. And that gives you the the optimal balance between the two factors. At high temperatures, it gets delayed because of lack of driving force for the transformation, and at low temperatures, sluggish diffusion. So this gives you some optimal stuff where the driving force is sufficient and diffusion is also sufficiently fast. But for the eutectoid steel in carbon steels, this nose, look at the time here, it is less than 1 second. And so if you take an alloy and start from the austenite region, then you can impose cooling rates on this. You can also draw cooling curves on this sort of stuff. So for example, if you cool it very, very slowly, for example, you put it inside the furnace and switch off the furnace, you are cooling the alloy very, very slowly because the furnace itself is cooling very slowly. So you are following a trajectory which is like that. It takes maybe about 2 to 3 hours for it to go from, let us say, 800 degrees Celsius to about 600 degrees Celsius. So we are traversing a path like that, very, very shallow path. And of course, if you quench it extremely fast at a rate of about 1000 degrees per second, then you are basically dunking it in water. And if it is a small piece, you can the entire piece can cool down to very low temperatures very quickly. But if it is a large piece, the surface gets cooled very fast, but the interior gets cooled later. And so you see a whole range of cooling rates. So it is possible to completely avoid these diffusional transformations by quenching things very, very fast. So it is possible to bring the austenite down to lower temperatures by quenching fast, but this austenite is still unstable. And what makes the steels interesting is that transforms through other means. So at temperatures below 500, this should be 550 degrees or so, they undergo something called bainite transformation. And of course, if you quench it down to extremely low temperatures, they also produce martensite, which is what I just want to show here. Bainite is another combination, another microstructural feature, just like pearlite. In the case of pearlite, they were alternating lamellae. And in the case of bainite, it is, okay, here is sort of bainite cluster, as it is called. And it is composed of plates of ferrite, which are all running parallel. There's a whole bunch of plates. If you do electron microscopy, TEM, and take it down to even higher resolution, you will be able to resolve each of those individual plates. And in the regions between the plates, you find these streaks of cementite. And look at the micron marker here. This entire thing is about a micron. So this cluster of plates is probably about 5 to 8 microns or so. And given the number of plates, the plates have a thickness of about 200 nanometers or so, which is pretty fantastic. I mean, I'll send you a link later for a researcher called Badishia at Cambridge University who worked on these bainites. He also wrote a book called Bainite in Steels, which he has made available for free on his website. And he is famous for developing something called super bainite. And the interesting thing there is that it has 0 carbon, so you don't find cementite, but you find extremely thin plates of alpha in a particular form. And that is known to have tremendous strength and so on, and it has found interesting properties. And I'll send you those links separately. Take a look at that. The other thing that happens when you quench it in water, that is, you have cooled austenite fast enough that it avoids the nose, and to a temperature low enough that bainite or pearlite is not possible, then it produces something called martensite. And this is a microstructure. The white region, this is from a very nice Flickr page that I found. This is the page of Zeiss microscopy on Flickr. They have a whole bunch of microstructures. Zeiss, as you know, are very famous makers of microscopes, including electron microscope these days. And we have several of their machines in our institute. I mean, electron microscopes. So the white region is the austenite, which is yet to transform. And all these other features, if you look at them closely, you can sort of discern some lens-shaped features. And so that is martensite. It has the same composition as austenite. Therefore, no diffusion obviously took place. Obviously, it also happened at extremely low temperatures where no diffusion could have taken place also. So this is a diffusionless transformation. Austenite with one crystal structure sort of changed without any diffusion by clicking into the crystal structure of martensite. That's the best way to describe it. Again, if you're interested, you can delve into it as a term paper. So this martensite is effectively a body center in steels with carbon. It is a body-centered tetragonal structure with a slightly a C/A ratio of 1.04. And as you can see, if it were 1, it would be BCC. And so that itself gives you a clue. It can be thought of as a supersaturated solid solution of carbon in ferritic iron. And when you pump about 0.8% of carbon into ferrite, which can hold only 1/40th or 1/50th of that amount in at equilibrium, it becomes extremely supersaturated, and so it acquires a tetragonal form. And that tetragonal form of ferrite, you can think of that as the martensite. So each lens of martensite actually, I mean, again, using microscopy, people have found that it is actually composed of extremely fine plates, which can be resolved only using electron microscopy. So this is an optical microscope figure. And so each of these is composed of hundreds of these extremely fine plates. All right, this martensite itself is extremely supersaturated. Therefore, if you heat it to some temperature where carbon can diffuse, again, you can precipitate out cementite, and the rest of, since the martensite is losing carbon, it slowly turns into cementite with time. And so this is basically a precipitation sequence, and this is called tempered martensite. Okay, last slide. So the versatility of steels is basically based on the huge variety of microstructures that you can produce using, again, a variety of heat treatments. You can go from extremely coarse pearlite, if you run the transformation at temperatures close to the eutectoid temperature, to fine pearlite, and the microstructural length scale here, that is the interlamellar spacing, is again about 1 micron and above. We have also seen coarse and fine bainite is possible at temperatures below 550 degrees Celsius, down to about 250 degrees Celsius or so. And again, the microstructure there has features whose thicknesses are of the order of hundreds of nanometers. And of course, at extremely low temperatures, you can produce martensite. Martensite itself is bad news because it's extremely hard, which is nice, but it's also extremely brittle because of the presence of carbon. There are also non-carbon martensites, which are not as brittle, but carbon-bearing materials, steels, which are quenched to produce martensite, they are never used in the fully martensitic form. They are always tempered. And when you temper them, you basically precipitate out carbides. And all these features can be further modified, and you can also introduce more customized heat treatments that become possible with the help of alloying elements. And this explains the huge variety of steels. There is one other thing that I want to mention, and I will send you appropriate links for videos on how these things are done. The role of alloying elements also makes it possible to devise, preferential modification of the material at the surface. And here we are producing a material with a mild steel, which and then you are preferentially introducing carbon at the surface, and that allows for a material eventually in surface which is hard at the surface and relatively ductile and tough at the core. And the best example use case for this sort of materials is gears in automobiles. So I'll send you links for some of these things. Those who are interested, you can look at them. Okay, that's a sort of half lecture summary of steels. We will move on to mechanical behavior from the next class onwards. This basically concludes chapter 10. And so the main things that I want you to learn in chapter 10 are all related to precipitation on the one hand, and eutectoid transmission and associated things in steels, including the TTT diagram. So the calister is relatively adequate for this purpose. Okay, we still have about 5 minutes or so. If you have any questions, we can take them up. So let me stop sharing the screen. All right, any questions?
So is there going to be a quiz tomorrow?
No, nothing. In fact, nothing this week. So we will cover a set of things, and I also have to give you some home assignment problems on this chapter.
Yeah.
So quiz will happen next week. So again, 2 quizzes. So that will take us to quiz number 8 and 9, and then we will run maybe 1 or 2 more. But don't worry, we'll still take only the 6 best ones. So Yeah, there is nothing tomorrow. So this week we will have 2 more classes, by the way. We are looking at least 2 more makeup classes. So that will happen this Thursday. And if we do a quiz next week, then we will have to do it some other. We'll make it up. So as I see it, we are probably looking at 6 more classes, maybe more. 6 or 7 more classes. 3 of them will happen this week. That is today, tomorrow, and Thursday.
Yeah, sure.
Anything else?
So what is the submission of term paper?
What is that? Come again?
What is the mode of submission of the term paper?
Yeah. So were you the one who asked me that question? I didn't even know that I have to create an assignment. So I will create one and then give a deadline, and you all submit it there. So I've never done it, so I'll figure out how to do it and create one. Don't worry. Remember 10th. That is a week from. Yeah, 10th is Sunday. I'm sorry. Yeah. 10th midnight is effectively the deadline for submitting your. That is the midnight between Sunday and Monday is the deadline for submitting your first term paper. And I'm sending you some instructions about how you can choose your second term paper topic. You announce it first, discuss it with us, and once we give you the go ahead, you start working on it. And for the second one, I mean, we will use your last exam date plus 4 days as a deadline. Yeah, I see one other. Anubhav Goswami.
Yes, sir. Are we going to have a traditional end-sem exam?
Yes.
Okay.
That will carry about 30%. We also talked about Viva that will be used for a part of the end-sem exam as well as a part of your term papers. So towards the end, I mean, after you submit your second term paper, we'll have a chat with every one of you for about 10 to 15 minutes or so, which will cover the stuff that you have said in your term paper, as well as, I mean, some general questions about from the course. So,
and so can you just tell me once the breakup of the weightage of these components?
We'll do that later. So,
okay.
Yeah, it's all within the 70% parameter that we are working with. 40% for the term papers and 30% for the end-sem exam. So if I'm going to take something from the end-sem exam and the term paper, it'll be of the order of let's say 5% each. So that will make it Viva will have about 15%. So something like that. We'll work something out. If you think it is unfair, I mean, we can talk about it.
Well, I would like a little less weightage for the quizzes, seeing as they are, you know, rapid.
No. Okay. The last set of, I promise that I will reduce the number. This multiple answer type, multiple possible answers type questions are a problem that I realized. I mean, I made the mistake of making both the quizzes heavily dependent on that type of stuff. I will reduce the dependence, but they still tell me one thing, and that is you are unable to figure out the, I mean, a substantial number of you have difficulty identifying true statements from statements that are sort of pretty ludicrous. So that, okay, that tells me something. I don't know what that is, but going forward, I can reduce the weightage for such questions, but they will continue to find a place in the quizzes. Okay, anything else?
Yes, sir. In the TTT diagram, doesn't like, I mean, I was thinking, doesn't the whole structure formation depend on the cooling rate? So
okay,
how do they plot it without considering the cooling rate?
Okay, I mean, the way it is done again is this 1 second is a bit of a pain, but the alloy steels, that nose is moved further out to tens of seconds, if not even hundreds of seconds. Okay, So in those cases, it is clean to explain. So you quench it in a quenching medium, which brings the temperature down to some desired value. Let us say 600 degrees Celsius. So these are, I mean, instead of water at low temperature, you are using baths. These are salt-based baths. They should not be reacting with the steel concerned, but they are all in the molten state, and so you dunk this little piece of steel into that. And remember, experiments are carried out using extremely tiny samples. These are very thin strips of the order of a millimeter or so, and you dunk it there, and you're reasonably sure that the cooling is instantaneous. Of course, no cooling is instantaneous, but you can start with that. And then immediately you leave it there. You leave a bunch of these samples there and take them out at regular intervals, 1 second, 5 seconds, 10, 20, 40, and so on. And quench it to low temperature, and then look at the microstructure and look at how much of perlite is formed or how much of bainite is formed. And that is how you determine the cooling curve. Like I said, it is experimentally determined. Given an alloy steel, given a steel with a specific composition, the holy grail, of course, would be to be able to predict the TTT diagram. We are not there yet. But no matter, you can always do this experiment, and for a huge number of steels. I mean, countless PhD students have toiled in labs to figure out their TTT diagrams. So there is even a handbook containing TTT diagrams, handbook with about 900,000 pages or so, and each page containing at least 2 TTT diagrams. So at least 2,000 different kinds of steels, their TTT diagrams have been determined to a reasonable degree of confidence. So they are all available. Like I said, countless PhD students, man. So they all toiled in labs. All this happened back in the day, 40s, 50s, 30s, 40s, 50s, 60s. So thanks to their toil, I mean, we have all that information now. But we know why they take on specific shapes. So, and the difference between plain carbon steels and alloy steels, all that is also known. So we can explain them, but predicting them from some underlying first principles stuff is extremely difficult because chemistry is hard. And here the chemistry that we are talking about is the interactions between the alloying elements, carbon, iron, and so on and so forth. So the more complex the alloy, the more difficult it is to come up with a scheme that will somehow predict things accurately. You can still predict broad trends. For example, you can predict things like, if I add a little bit of chromium, what will happen? I mean, that's a qualitative sort of understanding that we all have. But if you say I add 1% chromium, and how much farther out will the curve move to even within 10 seconds? I don't think we are at a stage where we can predict such a stuff.
Sir, and in the Martensite picture, or the microstructure picture, sir, over there we have like the lens-shaped grains,
right?
And there's like white, like backgrounds, like white color, right? So is that
is
like
austenite? That is still austenite.
Oh, okay, that's austenite. I mean, it looked like
untransformed austenite.
That's why I was confused.
Yeah, there are reasons for why some austenite remains untransformed, and the people working with steels, they know what to do about them, how to control the amount of austenite. Again, the triumph of empirical research, lab-based research, that is what led to this level of understanding, qualitative understanding. Quantitatively, I mean, like I said, the holy grail is to be able to predict what will happen under a given set of circumstances from something like first principles. The atomic numbers of various things, amount of various things, and so on, and somehow figuring out what is likely to happen. No, that is not possible. That level of theoretical understanding is extremely difficult to the present day. But empirically, these things have been determined, and people working with steels, they know how to control these things. For example, if you lower it to even lower temperatures, instead of cooling it in water, you cool it in water, you arrest all the diffusional transformations. Some austenite is transformed to martensite. You quench it further to liquid nitrogen, for example. You will find that some more austenite transforms, and but there is always some lingering austenite that would stick around. But it's known, and steel people, they know how to handle this stuff. So, okay, any other questions? We have already gone about 6 minutes over time. Yeah.
So with respect to the quiz 6 and 7, is it possible for you to include like partial marking in them, considering that like a lot of questions are like 3 marks each?
No. Let's not go down that. I mean, I am willing to concede that it was probably a wrong choice on my part to include only that kind of questions in those quizzes. Like I said, going forward, I will desist from doing that. But those questions will remain, and partial marking will not be there. Like I said, they tell me, they give me one piece of information, and that is that still a large number of you have difficulty identifying true statements from, I mean, blatantly false statements. Okay.
Yeah.
There are some ludicrous statements there, which are a dead giveaway. And I still see people choosing those as correct statements. That sort of worries me, but that's okay. Yeah.
So could we get the answer key for both the quizzes?
I will post the open versions of this again, just like I did in the previous case. Give me some time. I mean, I'm not there yet. I'll do that. You all have the answers that you've submitted, right? You all would have received some email saying that this is what you did.
So no, I don't think there was an option. I don't think there was an option of like
when you finish the quiz, doesn't it ask you for the same? Send me an email response or something like that. I don't know. I thought it was a part of most things. In Google Forms, for example, it definitely asks you, do you want to receive an email with your responses? I thought it was a standard thing here also, but if you didn't, anyway, I'll open it up. Don't worry. So
yeah,
I'll send you the open version of these quizzes. Okay. Anything else? We are well past the end time, so you're welcome to leave if you have something else to go to.